Hello and welcome back. I hope you had a good weekend. Thank you to everyone who uploaded their introduction video. Just being able to watch a 30-second clip of you telling me your interest and hearing you talk really helps me to see your personality and to make this whole process a lot more interpersonal. The relationship, I mean, there's not going to be a whole lot that we can do, but I will try to develop relationships as best I can this first quarter. Before we actually see each other in classroom. So that's very important to me. And so I thought I'd show you our classroom, which is waiting for us when we get back. So you'll notice we have all kinds of cool things that we use in geometry, like a straight edge and a compass and a calculator. If you are interested in getting your own calculator, you can look at the syllabus and I tell you which one you might want to get. They're like $15 on Amazon, the TI-30XS multi-views. It'd be really helpful. That way you don't have to use an app on your phone if you're using your phone for something else. It is possible to do the whole thing without having to purchase a calculator, but they are kind of nice to have if you're going to be doing all this stuff virtually like we are doing for the first quarter. All right, so let's go ahead and get right into it. So when we talked about an axiomatic system, there were three undefined terms that we start out with: points, lines, and planes. So a point is simply a geometric figure that has no dimension, meaning it doesn't have any width or any length or any depth to it. It's just merely a location. So here we have 3 points, just as an example. And point A, point B, and point C. They're usually indicated by the dot. That's the location or the point itself. And then we always have to label them. So if we haven't labeled them before, it's still a point, but as soon as we label it, this is now point A, okay? So another thing is, even though you see that this is it's a dot, it's a circle, right? It's a filled in circle. It's actually the very center of that filled in circle. That's the location, point A. This circle, it has a thickness to it, right? But if we're just indicating the point, then that would be an infinitely small little speck, or like an atom. You can think of it that way. So anyway, this is point A, point B, and point C. We annotate those, like when we're writing in a sentence, we refer to it as point A, point B, or point C. There's no dot on top of it or anything like that whenever we're dealing with annotations. The next one is a line. So a line is a geometric figure that has one dimension. It has a length. And technically a line extends forever, so it's an infinite length. So it extends forever in opposite directions along a straight path. Now, we talked about non-Euclidean geometry when we reject the fifth postulate. That would allow lines to curve and planes to no longer have to be flat. But we're only going to deal with Euclidean geometry for this year, maybe at least till the end of the year. Then we might do some more non-Euclidean. But anyway, so here we have 3 lines connecting any two of those 2 points. So line AB would be this red line. It goes directly the straight distance between A and B and extends past B and past A as well. And that would be annotated AB. Notice we have a line symbol over the top with 2 arrows. So you'll notice a lot of this stuff you've actually heard from middle school before. So there's not a whole lot of new stuff here. We just need to go into it. And this is really the foundation of all of what we're doing in geometry, the vocab. So let's make sure we have it down. Then we have line BC and line AC as well. And those are color-coded for you as well, so you can kind of see what's going on. Our third one is a plane. Now, a plane has 2 dimensions. It's a flat surface that extends forever in 2 dimensions. It has a length and a width, and extends forever in all of those directions. So it doesn't have a thickness to it. It's not all of space, but it's a flat surface that extends in 2 directions. So, for instance, we could annotate, and we always have to notate a plane with 3 non-collinear points. And we'll talk about non-collinear a little bit in a second. So if we have plane ABC, we look at points A, B, and C. So if all 3 of those points were on, I guess I'll go ahead and tell you now, if all 3 of those points were on the same line, then we wouldn't know what surface we were talking about, right? Are we talking about the top surface or the top face? Or are we talking about this left face over here? So it's important when we define a plane, we use 3 non-collinear points, which means that they're not on the same line. So I'm going to move C back over here where it actually was. So plane ABC is referring to this top surface here. Now keep in mind, I'm using a cube here so you can see the 3 dimensions, the depth as well, and the length and the width. But really a plane is not actually the square or rectangular surface. It actually extends forever and it keeps going. to the left and to the right and back and forward. So even though we're only using this rectangle to draw it out, remember it actually keeps going forever. And that shouldn't be new to you. We've actually, when we're talking about planes before, like with a Cartesian plane, we know that those extend forever as well. So think of it in the same way. So over here, remember our Cartesian plane with the origin at 0, 0. We have our x-axis and our y-axis. Why do we have these arrows here? That's because we know that it extends forever, right? So even though we ran out of space at 6, we know this plane keeps going on forever and ever to positive and negative infinity. Same thing on the x-axis. It's going to keep going forever, and the x forever for the width, and to positive infinity and to negative infinity. So when we're talking about the plane, like this front surface here, the front face of the cube would just be that square, right? But if we're talking about the plane that faces on, that would be the plane. We'll say BCG, or we could do BFG or GFB, whichever three, as long as they're not on the same line, it'll work. That plane actually keeps extending forever in those directions. So let me go back so you can see some more of what I'm talking about. So for instance, this is plane ABC. We annotate it. There's no special symbol for it, just called plane ABC. If we want to refer to the plane on the bottom, okay, remember, it's going forever in all two of those directions, or all four. It's really 2 dimensions though. We could call this plane EHG or GHE or EFG or GEH, whatever 3 points we want to use, as long as they're not on the same line. Now we also have the other surfaces here. So we could have plane CDH or CGH. We also could do the plane on the far left here. Okay, so that would be plane ABE or EFB or whatever else we really want to do. So anyway, that's a plane. So we have points, lines, and planes. Let's go over that again one more time. So a point has no dimension. It's just a location. Between any 2 points, we would have a segment, but if we extend it forever, that would be a line. It has 1 dimension, which is length, even though it's an infinite length. So that's a line. And then a plane has 2 dimensions, length and width, but not depth. So there's no thickness to a plane. It's infinitely thin, right? So it's just like a point has no thickness to it either, right? It has no dimensions. But a plane has 2, length and width, and remember, they extend forever in both directions. So it keeps going forward and back and up and down. The same thing with the plane on the bottom. All right, a segment. So a segment is a collection of all points between 2 endpoints. Technically, collection of all collinear points between 2 endpoints. I'll go into that more tomorrow. Today we'll just define as part of a line that has 2 endpoints. So we could do segment AB, segment BC, or segment AC, just in any 2 endpoints that we have here. Now if you notice with our annotation, what's different is we no longer have the arrows over the top. So if I'm referring to segment AB, that's going to be all the collection of all collinear points, all the possible points that are on the same line directly between A and B. That would be segment AB. Segment BC would be the segment with endpoints at B and C and all the collinear points, possible collinear points that exist in between those 2. And then AC would go all the way from A to C. So it would be a collection of all collinear points, including B, that are strictly between A and C. So that would be a segment. We have a ray. So a ray has 1 endpoint. It's also part of a line, or you could say it's half of a line that has a starting point and it goes in a certain direction and extends forever. So here we have 3 rays that are easy to see, at least, annotated BA, BC, and BD. Now when we're reading a ray, again, look at the symbol. We have a starting point, so there's no arrow on this, but then there is an arrow over here. So we always start with the first letter, and the second letter always tells us the direction that it goes. So BA starts at point B, and it goes in the direction and through the point A, but it also keeps extending forever because it's not just a segment. So that would be ray BA. BC is going to start at B and go through the direction of C, the point C. So BC is ray BC is going to be this ray right here. Remember, that keeps going forever. And then BD starts at B and goes all the way through D and keeps going. So it's all the collinear points from B to D and beyond D as well. I don't know if there's anything else. Oh yeah, there's also 2 more rays here that you might be able to see. So one of them would actually be this ray right here. What would you call that ray? The red one there. Not just the red one, but what would you call it using the points? Where does it start? Well, it starts now, instead of at B, it starts at point C. And then what direction does it go into? Well, you could either call it ray CB or you could call it ray CA. Really, it would have two names. It doesn't matter which one you want to use. The other one that we have here, I'll have to bring this to the front, or rather I'll just bring this one to the back. Anyway, the other one that we could do would be AB or AC. So this is ray AB or ray AC. Again, it doesn't matter which one you use because those are collinear points. As long as it's starting at A, it would be the same definition. But when we're referring to annotating rays, the order matters. It's very important. So if we're talking about, if we read this, this is ray AB. We always start where the ray starts, which is A in this case. So which one of these two rays, the blue or the green one, is ray AB? So which one starts at A and goes through the direction of B? Well, that would be the green one, right? So the blue one is actually called ray BA. And notice, even though it would be backwards, we read this BA, not AB, when we're starting at B and going through the direction of A. So what I'm trying to say is we never would flip this and draw one like that. Let me do it like that. That way you can see what I'm actually trying to get at. All right, so this would be an improper way to annotate array. I see what you're trying to do, saying you start at B, then you go to A, but the problem with that is we always read left to right, right? Unless it's, I think, Arabic or a few other languages that read right to left, but we always read left to right. So if we're referring to this ray here, that would be ray BA, the blue one is BA, and we'd have our arrows going always from the left to the right. There we go. All right, so it can be a little tricky, but that's really important. The green one would be referred to as AB, and the blue one would be ray BA. Because again, we always start at the end point, and then the second one tells us the direction that we're going. Opposite rays. So opposite rays are two rays that start at the same endpoint, and they go in opposite directions. And they form a line when we add them together, okay? So two rays that share a common endpoint and go in opposite directions. So in this case, our two rays, our opposite rays would be let's say ray BA and ray BC. Now these are opposite rays because they both start at the same endpoint B and they go in opposite directions, A and C. And if we added those two rays together, they would add up to a full line. Now we would not refer to a ray. Let me see if I can grab one here. Okay, I'll just draw another one. That would not be an opposite ray. So I would need a point here, so I could make another point real quick. Showing off my smartboard skills. Anyway, so ray BD and ray BA are not opposite rays. They form an angle. It's not a straight angle, right? That's because they don't go in opposite directions like the other two do. Collinear points. So when those are points that are on the same line. But to remember that, let's just break down the word. What does co mean? So co means together, okay, and linear, or co also means same, I'm sorry. Linear means line, or same line, right? So collinear means points that are on the same line. And that's how you remember. It sounds like a fancy word, but it's really not that bad. So on this one, here we have points A, B, and C would be our collinear points because they're all on the same line. D is not collinear with A, B, and C because it's not on the same line. But if I move D so that it was down here, now they would be all four collinear points. Coplanar, just like collinear, means that it's on the same plane. So these are lines that are on the same plane. So for instance, I don't think I brought any. If we're talking about this top surface here, coplanar lines could be AD or AB or BC and CD. All four of those lines are all on the top plane. So they would be coplanar lines. All right, intersection of two lines. So let's say we have two lines. We'll start out with BF and we'll do AB. So do those two lines intersect? Yes. What is the intersection of those two lines? Well, these two lines intersect at point B, right? Okay, so the intersection is point or points that two or more figures have in common. When we intersect two lines, if they do intersect, it's going to give us a single point. What about these two lines? They intersect. Yeah, so FG and FB intersect at point F. intersection of planes. So let's look at the surface here. I guess I'll put it on the top. And then let's look at the right surface right there. So here we have two planes. We have our top plane, which is plane ADC. And we also have our right plane, which is CDH or CDG, whatever you want to call it. What is the intersection of those two planes? Well, they do intersect. They're not parallel planes. And their intersection is going to be CD. But on this one, we have to be careful. It's not segment CD. It's actually line CD. Because remember, these planes are not just the rectangles or square surfaces. They extend forever in both directions. So their intersections are also going to keep extending forever in both directions. So the intersection of two planes is going to form a line, not a segment. Because keep in mind, they are going to keep intersecting, right? So this one's going to keep going backwards and forward, and the same thing with this plane up here, causing that intersection to keep going on forever, forming that line, and keep going on forever, forming this line over here. All right, parallel lines. Parallel lines are coplanar lines that do not intersect. Once again, what does coplanar mean? Same plane. So two lines that are on the same plane that never intersect. So are any of these three lines, are they parallel? No, none of those are parallel. Why? Well, these two are coplanar. So the blue and the green are coplanar, meaning they're on the same plane, they're on the front surface, okay? But they do intersect. So those are not going to be parallel lines. And then the green and the red, they're not on the same plane, right? This one's on the front and the top surface. This one's on the bottom and the right surface. So they're not on the same planes. So they are actually going to be called something else. But if I move a green one from here back to here, are those two green lines parallel? Yes, because they're on the top surface. They're coplanar, same plane, and they don't intersect. And also, if we move this down here, those green ones would be parallel. And also these green ones here, struggling a little bit. So any one of those two green lines would be parallel. And we could do the same thing with the red ones, right? So those would be parallel. Those red ones are parallel, and the same thing with those. And the same thing if we did it with the blue ones. So all the blue ones are parallel as well. All the red ones are parallel, and all the green ones are parallel. That is a busy diagram. All right, moving on. Skew lines. Skew lines are slightly different than parallel lines because they are non-coplanar lines that don't intersect. So both of them don't intersect. One of them is coplanar, is parallel, and one is non-coplanar, which is skew lines. So essentially, if I took two lines here, the two red ones, do they intersect? No, they're parallel. But if I move one of them, move this point, yeah, so this is kind of how I remember it. If you take two parallel lines and then you twist one of them, that will make it a skew line. So if I took this line here and I twisted it, and I've got another one here just because it's another color, make it a little bit easier. Now they are skew lines. Let me move this one back down here. They're skew because they are not on the same plane. One of them is on the bottom and the right plane. This one's on the back or the rear and the top plane. So they're not on the same plane, and they also don't intersect. So it's kind of like two parallel lines, and then we twist them. Essentially is what's going on here. If I did the same thing with the blue line and I moved it up here, they're still skew, right? Because they're not on the same plane, they're non-coplanar, and they still don't intersect. Same thing would happen if I move the red line down here. Okay, the red and the blue are still skew. If I move this one back here, they're still going to be skew. They're not intersecting, and they're not on the same plane. All right, space is pretty simple. It's a collection of all possible points. So all of these points that you see here, all 8 of these vertices or vertices for the cube, they're all points in space. But keep in mind, there are even more points that exist in space. In fact, any point exists in space. You put a point here, or there, or there, or there, or there. You can put it on the inside, you put it on the outside, put it above it, put it below it. All of those points exist. We would just simply have to give them names. So this would be point R, this would be point J, this would be point I think I already have an F, so let's do, I didn't do a point I, so that would be point I. So all we have to do to make a point is just to point it out and then give it a letter for a name. All right, so that's it for the lecture for today. We'll go over some more of our vocab tomorrow, or just go more in depth tomorrow. So 20 minutes, that might be a little on the long side. Hopefully we'll be able to speed those up for you. So if you'll go ahead and get out your assignment, what you probably want to do is open the assignment in Google Classroom as a PDF. You can either print it off if you prefer that, or you can edit it and mark it up in the PDF editor right inside of Google Classroom. So you want to do that probably on your iPad, and you might want to move the video to your phone or another device that you have, or a computer screen or something like that. All right, so let's look at number 1. So we're going to solve a riddle. If you read the instruction there, it'll tell you what the riddle is. So the first thing is we want to know if the statements are true or false. If they're true, we take the letter that corresponds with it and put it down on the bottom to answer the riddle. If it's false, you can just cross it out or whatever, and we're not going to use it. So the first one says that line CK, and I know it's a line because it goes in both directions with the arrows. Line CK intersects line RL at point O. So CK is here, and then RL is here. See if I can actually just change the colors on those. All right, so I'm going to color them so we can see what's going on. So CK is the green one, RL is the blue one. Do those two lines intersect at point O? Is that true? Yes, it is true. So you could circle it if you want. It doesn't really matter to me, however you want to do it. And then we're going to move the E, which corresponds with 1, down to our first letter. All right, next one is number 2. Point M lies in plane X. So if we look over here, the X doesn't have a dot next to it. So this is point K, but this is referring to the plane itself. Typically, we define planes with 3 non-collinear points, but if you see a letter by itself without a point next to it, then that's referring to the plane. So plane X is going to be this rectangular surface here, and keep in mind it's not the rectangle that actually extends forever, but so we would probably put arrows on it. So does point M lie in plane X? So if you see these dots here, that's actually telling you that this part of the line is behind the plane. So that's what the dots are. And I'm assuming that point M is going to be below the plane as well. It kind of looks like that, even though this surface could extend out and like M could be on the same plane. But I'm going to assume that it's not. I think that's kind of what they were trying to describe. So I'll cross out A. Next one, are points ROK and A coplanar? So ROK and A. All right, so RO and K are on plane X, but A is above plane X. So all 4 of those are not going to be coplanar. And in fact, you can't make a plane that has all 4 of those points. So that one would be false. So we can cross it out. All right, then ray OR and OK are sides of angle ROK. So OR and OK are parts of angle ROK. Yes, that's true. So our second letter would be U. So you can circle it if you want, or however you want to do it. And E and U. We're going to end up spelling out that word. Okay, so look at 14. That's going to be the second column. These are, I color-coded them green for you. This is going to be on the second word. So the first column's for the first word, and the second one's for the second word. So we're also using this different diagram, so I want to show you an example of that. So now we have ray in J and ray in H are opposite rays. So remember, opposite rays start at the same point and go in opposite directions. So here we have ray in J, so N to J, and then N to H. So they start in the same point N, and they go in opposite directions to J and to H. If we put them together, it would form a line. So that one is true. So you can circle it if you want, and that will be our first letter. It's E. Second one says that line ZL intersects line RO at O. So we have line ZL. Where is ZL? Could this be a typo? Okay, so that's actually using the other diagram, which is totally fine. So ZL is going to be this line here from Z to L, which even though there isn't a line shown there, you can always draw one. Remember, that's one of our postulates, kind of one of our assumptions. So I can draw a line from Z to L. That'll work for me. All right, so there, it exists now. All right, so we have ZL and RO. So RO is going to be the blue line, and then ZL is going to be the black line. Do those intersect at point O? No, they intersect at point L. So that one would be false. So we can cross it out. And then we have segment GF intersects line JH at N. So GF, which is going to be this segment here from G to F, but only the points in between it. It's not extending forever because it's just a segment. Does that segment intersect JH? So JH is going to be this segment here. I'll go ahead and color it for us, the green one. So the green one and the blue one, do those two intersect at N? Yes, that is true. So that would be our second one. That's true. So E, and then we'll do L. All right, so you'll end up spelling that out. It should actually spell something. If you didn't get it, if it doesn't spell something, you probably can figure out what it is supposed to. But go ahead and try it out first, and then play the game and figure out if you got it right. Okay, look at number 26 on the back side. It says for I need to update that, but anyway, for number 26, we want to determine whether a statement is always, sometimes, or never true. These are tough problems, some higher level thinking, but you're an honor, so you can do it. I'm really testing whether or not you understand the ins and outs of these vocabulary words and these concepts whenever I ask questions like these. So try them out. We'll do 2 of them together, and you got your answer bank on the side here, as we will for all of our problems where appropriate. All right, so the question is 3 points define a unique plane. Is that always true? So 3 points define a unique plane. That's close, but let's look at it. So if we have points A, B, and C, does that tell us exactly this whole unique plane means there's only one? Is there only one plane that goes through these 3 points A, B, and C? Yes, that's true. We know we're talking about that rear surface, right? That rear plane. But does this point C, does it have to be on a different line? What if the 3 points A, B, and C were collinear? Now does it find a unique plane? No, because we don't know if we're referring to the back surface or the top surface, right? So it's important that our 3 points that are defining a plane are non-collinear. Then it would be a true statement. That's always true. So sometimes 3 points will define a unique plane when they are non-collinear points. But when they are collinear points, like A, B, and C are here, if I can actually reach it, there we go. Now they are not defining a unique plane. They could actually define infinitely many planes. And let me try to see if I can draw that out. So along this line that we have on the back here of ABC, line ABC, the plane ABC is technically allowed to rotate 360 degrees, right? Could be the back surface, could be the top surface, it could be any plane that rotates around that line 360 degrees. So technically there are infinitely many planes that exist with points A, B, and C on them if they are collinear points. So it would be it's not a good way to define a plane. It's because it's not a unique plane, because it would be allowed to rotate. It still has that degree of freedom. So this answer here would be sometimes true. So you can just write S for sometimes if you're super lazy like I am, and understand you're writing maybe even with your finger on the iPad, so it's not a lot of fun to write. All right, 28. AB and BA are opposite rays. So it looks like on this one I forgot to do the symbols for that. So we have ray AB and ray BA. Okay, so are those opposite rays? Well, AB and BA sounds like they're just opposite and backwards, but what's actually happening here? So if we have points A and B, ray AB is the green one and BA is the blue one. Do they go in opposite directions? Yes, but in order for it to be an opposite ray, they have to start at the same point and go in opposite directions. But these are not opposite rays because they start at 2 different points. So this is never true. We found the one that was never true. All right, 31 through the end. It should be pretty simple here. Starting out easy with your first assignment, except for those last problems we did. Those are pretty tough, but you only got 3 more to try out. All right, shade or sketch the pair of figures. You don't have to do that. So just name their intersection. So, shade or sketch. Yeah, I see what that's saying. All right, so planes ABC and CDR. So plane A, B, C is going to be referring to the top surface. So I have mine shaded nice. If you just want to shade it just kind of like that, that works totally fine, but I just wanted to have something nice to look at, okay? And then we have plane CDR. So CDR is going to be the front one. So if you just want to shade those planes like that, that's totally fine. Also remember that they're extending forever in all four directions. So usually when we shade planes, we also are going to draw the arrows so that we can see that they do extend in all four directions. But that gets a little messy, so I shaded it in like this. All right, so what is the intersection of those two planes? Well, they're not parallel planes, so they do intersect, and their intersection is going to be DC, but not just segment DC, it's actually going to be line DC, because the intersection is going to keep extending on forever. Because this plane, remember, this plane is going to keep extending forever in that direction, and this plane extends forever in that direction. So as they keep going, they're going to keep intersecting. Same thing in the other direction, because that plane keeps going to the left, and this one keeps going to the left, so does their intersection. So the intersection between these two planes is going to be CD. So we're going to go ahead and annotate that as CD with a line over the top, because it is a line. So our answer would be line CD, and we've annotated. What about line AD and CD? So I think this is the last one we're doing today, so almost done. So AD is going to be the line up top here, so just draw the line extending forever. And then CD going to extend there as well, so just kind of draw over them if you want. And then the intersection of those two is going to be point D. So the answer on this one would be point D. And then just go ahead and draw it on the diagram. All right, so that's it for today, just 32 minutes. You pretty well have all the rest of the time to work on your assignment here. So as soon as you get done, you can upload it to the Google Classroom. Technically, it's due today by midnight or whatever, but you can work on it anytime that you want. So if the sooner you get them done, the sooner I can grade them and give you feedback. I will say most of you guys have signed up for Remind. If you have questions or you want me to, if you're struggling on a problem or something like that, if you comment a private comment in the Google Classroom, I'll get around to it and I'll be able to answer it whenever I grade it. But those comments and notifications get lost, and so if you need to get a hold of me, use Remind. That goes directly to my phone like a text message. So I'll be able to read it and get back to you shortly if I'm not busy. Okay. So if you do have questions, don't be afraid to bother me on Remind. I prefer that rather than just posting something on Google Classroom in the private comments, because those get lost, and if I don't respond to in Google Classroom, it's not that I'm ignoring you, it's just that I'm not seeing it. Okay. So we'll use Remind for anything like that. If you need to get a hold of me for questions or something like that. Okay, so hope you guys have a good day, and I'll see you tomorrow. Bye bye.